Hello, Algebra 1 students, and welcome back to Topic 7. This is actually your last lesson in Topic 7, which is, of course, quadratics in vertex form. However, don't think you're done with quadratics. We actually have 3 more units on quadratics. We barely scratched the surface. It turns out there are 3 forms of quadratics. We did vertex form for this unit, and then we're going to try and fill in the rest of the pieces over the next 3 units. Today's lesson is actually on 2 different concepts, but strangely, they're already concepts you know how to do. And so hopefully everything we go through today will seem familiar to you. And the nice part is if you didn't learn it the first or second time that you heard it, you're going to hear it again today, and you'll hear it at least once for every other unit for this semester. So eventually it's going to click. However, if you want to learn it earlier, like now, and you're still stuck, make sure you ask your teacher because it does come back around over and over again. So, without further ado, let's get into key components or key features of parabolas and the average rate of change. We should know by now that parabolas are the graphs of quadratic, remember think quadra, square, quadratic equations. Alright, so let's go ahead and graph this equation right here. It's an HK form, vertex form below. And then after we've graphed it, we're going to try to define or label each of these features. Okay, so you should be able to do this, but I'll talk you through a bit of it. The vertex isn't bad, 3, -4. We've done that several times. The axis or line of symmetry is that line that goes right through the vertex. It's that line you could fold your paper over, and it would mirror the parabola onto itself. And so that's just going to be x equals 3. Okay, we can also remember there's that invisible slope out front, 1/1. That gives us 2 more points. And actually, we usually include 5 points, and to do that, we need the Y-intercept. So to find the Y-intercept, since we're using function notation, I'm going to say f of 0. That just means replace our x with 0. We'll follow PEMDAS, so 0 minus 3 is -3. I'm going to need a new line. I'll keep the f of 0, though, to show what we're finding. We have -3 squared. -3 times -3 is +9. And 9 minus 4 is 5. So what did we make? Well, we input 0 for x. We got an output of 5. 0, 5 is way up here. And that's where that axis of symmetry comes into play, because now I can count 1, 2, 3 in, 1, 2, 3 out. And we have a pretty good parabola. Now, this does ask us about the X-intercepts, which is something we haven't covered this unit. We've done it in the past, but not this unit. So let's go ahead and just try and sketch in this parabola and see if we can figure out where the X-intercepts are. Something like this. Now, as a reminder, of course, the X-intercepts are where the graph intercepts or crosses the X-axis. So it looks like we cross here and over here. So we would write those points, there are 2 of them, aren't there? 2 places where we cross, as some number, 0, and some number, 0. But the question is, zooming in here, what is that number? Now, many of my students said, oh, well, you're just a bad artist, Mr. Grant, and they're not wrong. This is actually 1 and 5. And I said, you've said some true statements and you've said some iffy ones, because how do you know it's 1 and 5? There are certainly parabolas that cross at a little bit smaller than 1. Maybe this is 0.8, and maybe this is 5.2. And I challenged them, and I said, can you prove to me that they cross at 1 and 5? And a few students said, ooh, I bet you could at least substitute in 1 and 5 to the original equation, and maybe get 0 as an answer to prove that those are the X-intercepts. And they're right. But that's a little tedious to take a number, plug it in, do the math, find 0, then take the next number, plug it in, do the math, find 0. And so the first thing we're going to focus on today is how can we determine where exactly those X-intercepts are? And hopefully you remember, because we've done this, I think at least 3 times now. We did it with linear equations, we did it with linear absolute value, and with exponentials. So let's get to it. Due to parabolas not having a constant rate of change, right? They're curvy, they change their steepness everywhere. It can be tricky to use the a value to find more points. right? And if the a value doesn't work out perfectly with the x-intercepts, it can be really tough. Well, if you consider the format of a quadratic equation in vertex form, I have it right here, we already know how to find the y-intercept, right? That's where you take x and you replace it with 0, and that leaves you the value of y. That is the y-intercept. And we've learned in the past that if we wanted to find the x-intercept, we pretty much do the same thing. But we don't replace x with 0. Now we replace y with 0. It looks like a 6. There we go. Once we replace y with 0, our goal here is to find the x. And so to find the x, you're of course going to follow SADMAP, which is exactly what we did in our last lesson, 7.5, right? That's where we have to undo a square with a square root, and there's 2 answers, right? This kind of all fits together really, really well. The reason that we spent so much time last class on 7.5 was so that we can isolate x to actually find the x-intercepts. In fact, because when you're dealing with a quadratic in vertex form, you replace the y with 0 to find the x-intercept, you oftentimes hear this process called finding the zeros of an equation. So if someone says, I'd like you to find the zeros of this quadratic, what they really mean are the x-intercept. And if you want to notate that on your paper, that's probably a good idea. There we go. So we're going to try 2 examples. Please go ahead and list your answer as an exact value, that means no decimals, and an approximate value if necessary. And you'll see what that means, I think, when we get to problem 2. But let's start with problem 1. And hopefully this is familiar. It's the same equation as up above. We start by setting y to 0. And then, as a reminder, we just follow SADMAP. Right? Let's identify everything that's attached to x first. We've done this before, but it's good practice. There's a 4 that is subtracting. There is a 2, which is an exponent. And then there's the weird one. There's the 3, which looks like it's subtracting to x. It is, but we can't get to it yet. It's locked in the parentheses. And the parentheses are way at the bottom here. So before we even get to the -3, we need to undo everything else. So let's go ahead and undo subtracting 4 by adding 4. Like so. That gives us 4 equals x minus 3 squared. That took care of the subtraction. There's no addition, multiplication, or division. Now we undo the exponent. This was our new stuff from earlier. Plus minus, plus minus. And because we're so comfortable with square roots, we know the answer to 4 is 2. The square root of 4, that is. X minus 3 is here. And don't forget the plus minus. Last but not least, we can finally get to that -3, and we can undo that by adding 3 to each side. And because we're so well practiced at this, we know the answer is not 3 plus 2 to get 5, but rather it is 3 plus -2. And we discussed a bit last class, and hopefully you've practiced in the meantime, that to see our 2 answers, it's quite often easiest to make 2 equations here, where one is 3 plus that 2, to get 5, and the other is 3 with the -2 to get 1. This 1 and this 5, the zeros, actually form the point. 5 for the x, 0 for the y, remember the 0 up here, and 1 for the x, 0 for the y. And so what that tells us is on our parabola back originally, Mr. Grant was just a poor artist, and this really should have gone through 1 and 5 exactly. We can be a little bit more accurate this time and go through here, and I still pretty much missed the point. Whoops. Okay. Let's try one more. What are the x-intercepts for the second one? Well, to find x-intercepts, we always start by replacing y with 0. Nothing terrible, and then again we'll follow SADMAP. So I'm just going to identify how they're attached: subtraction, multiplication, exponent, and the last part is the parentheses. Let's undo the subtraction first. We add 16 to each side. And again, if you're at that stage where you don't need to show the plus 16 on each side, you just know it's 16, please feel free to skip to that. You don't need to show the extra steps. You've only done this half 100 times, if not more. Next up, divide off the 2 from the multiplication. Gives us 8 equals x minus 1 squared. Undo the square. Square root with the plus minus. Those cancel. Leaves us with, what is the square root of 8? Don't say 4. 4 times 4 is 16. 3 times 3 is 9. 2 times 2 is 4. Whoops, I went from 9 to 4. I didn't hear 8 there. I don't think 8 has a nice square root. You can always double check that on your calculator, but for now I'll just keep it here. Equals x minus 1. And we'll finish by adding 1 to each side to give me, I'm going to switch the x over to the left just because it makes me happy, 1 plus minus the square root of 8. Now there are a few things here that we should probably realize. First, the square root of 8 reduces. So that factoring sheet we got on 7.3, let's go ahead and reduce the square root of 8. My students, per usual, seem most comfortable with this tree method. Okay, we're going to take that pair of 2's, goes on the outside, and then we take our little loner leftover 2 hanging out right there, goes on the inside. So that gives me the answer, x equals 1 plus minus no longer square root of 8, but now 2 square roots of 2. So we have one answer here, that is correct. We have another here, that's correct. But what if you were asked to plot these as x-intercepts? What would you do? Well, 1 plus 2 square roots of 2 could be a little tricky. You know it's bigger than 1. It's probably bigger than 3, honestly, 1 plus 2. But where exactly? And so what I like to do is, again, split this into 2 equations. X equals 1 plus 2 square roots of 2, and x equals 1 minus 2 square roots of 2. And then we're actually just going to find the decimal equivalents of these. And we don't do this too often. The reason, again, we're doing it now is because a single decimal is going to give us a much better indicator about where these x-intercepts will go. So you do need a calculator. But the nice part is typing this into the calculator is not bad at all, right? We're going to go through and just switching things over and just literally type each of those into your calculator. So I'm going to go through, get that calculator on, and I'm going to do 1 plus 2. Not a bad idea to put the times in between. And then we have that square root of 2. Hit enter, and we get 3.828. Most calculators, by the way, will let you go back up and copy something you've previously done. So that way I can just go over and change the plus to a minus and see the other. You'll notice some symmetry, and this is very common with our quadratic zeros, that they have the same decimals at the end. And we'll talk more about why they have the same decimals in the next couple units. But for now, it is a very common sight. So we got that 3.828. Remember, we always got at least 3 values past the decimal. We're practicing for that AP calculus in the future. And negative 1.828. So if you were asked to graph these x-intercepts, then you would go almost to 4 and almost to negative 2. And that should be pretty accurate for those x-intercepts. All right. Well, last 2 things before you get some practice in. We discussed before that zeros are the same thing as x-intercepts. So what if somebody asked you how many real zeros, you could just think how many zeros can a parabola have? Well, you're actually going to need 3 little xy axes here, and they don't have to be perfect. Mine certainly aren't going to be. 1, 2, 3. And we've already seen one option. We saw, just from this first page, that a parabola could cross in 2 spots. Now on the first page, mine crossed there. Just to show you it could be different, I'll do something like this. Here's a parabola, and notice that this parabola has 1, 2. This parabola has 2 zeros. So what this question is asking you is, are there other options? Could a parabola have 3 zeros, 4, 1 zero, none, negative zeros? Does that even make sense? So think on it for a quick second. Sketch in your responses. There are 2 more we haven't done. And then we will share out. Ready, set, Go. All right, well, hopefully you came up with the other two answers. There is a chance for a parabola to only have one zero, and there is a chance for a parabola to have no zeros. Could you picture what they are? Well, 1, 0 isn't bad. It's just going to come down. It's going to just really bounce off that x-axis. Can we see the single 0? You could have also just drawn one that looked like this. You don't need both of them, just one of them, but I'll put or. And then no zeros? Well, that would just be a parabola that's floating up here, right? It never touches the x-axis. The other option, of course, is it could be floating below. Now, remember that your vertex form equation for a parabola looks like this. Do you think you'd be able to use this vertex form to predict how many zeros your graph has? And it's actually a bit of a complicated question. Let's take a look. Well, the first scenario I'd ask you to imagine is when k is 0. If k is 0, then that gives you y equals a times x minus h squared, which means that your vertex is h comma 0. What do some parabolas with h comma 0 look like? Well, you could have a vertex h comma 0 right here. Maybe it goes up. You have a vertex with h comma 0 over here. Maybe it goes down. But I think h comma 0 is going to put you right on the x-axis, and that's only going to be a single 0. Well, maybe compare that to something like this, where a is positive, and I'm going to write that like this, a is positive and k is negative. What do those graphs look like? Well, if k is negative, then that means my vertex, right, this part of my vertex is negative. That means the vertex is a negative part of the y-axis. Here's a negative k, here's a negative k. Any of these could be negative k's. But if a is positive, which way does our parabola go? Well, our parabola goes up. And so, how many zeros do you see here? Well, I could do that with any of these, couldn't we? How many zeros do you see? Well, I see 2 zeros every time. So just as a bit of a bonus or an extension question, could you think about what would have to happen to give a parabola no zeros? Well, hopefully you realize that this same situation would work, but I think a would have to be less than 0. And if that's the case, the parabola starts in the same spot, but goes in a downward direction. There are other options too, but it just gives you a nice indicator of how a and k work together to create those x-intercepts. So, at this point in time, we have enough knowledge to create a pretty darn accurate parabola. In many cases, it's a parabola that will have 7 points, sometimes just 5 if they overlap. So, we have 2 quadratics, one on this page, one on the next. Your job is to graph them as accurately as possible, and then create the graph for the parabola including as many points as possible. So follow the steps. It goes A, B, C, D, E, F, all that fun stuff. Get it graphed. If you get stuck, unpause and check or listen to my walkthrough. If you're in class, please work with a different partner for each one of these, which one partner helps you with all of one, the second partner helps you with all of problem 2. And then whenever you guys are ready, unpause my video and see how you did. Ready, set, go. Alright, let's get to it. Problem 1. Given this equation, let's state the vertex opposite of h, comma k. Negative 3, comma 4. I'm just going to do a piece at a time. B, state the axis of symmetry. That always passes through the vertex. Notice it goes through the x-axis at negative 3, and it matches the vertex over there. State the a value as a fraction. Well, there's that invisible 1 hiding here. And so that gives us negative 1, and a is always written over 1. That even lets us find 2 more points. Down 1 to the left 1, down 1 to the right 1. Find the y-intercept. Well, to do the y-intercept, we always replace x with 0. And by the way, if you're doing this on the test, you do always need to show the setup. This is the setup. Now from here, you could put all of this into your calculator and come out with the answer. However, for any problem, we need to see what you started with and then your answer, just so we can make sure you didn't set things up incorrectly. So we get negative 3 squared plus 4. That's negative 9 plus 4, which I think is negative 5. It's always a good idea to see if this actually makes sense on your graph too, right? If the y-intercept was 4, that wouldn't make sense. That's not a U-shaped graph anymore. 3 wouldn't make sense. It can't just go straight sideways. 0, negative 5, though, actually does make sense, right? If we follow this down, looks like it makes a nice U. 1, 2, 3 away, 1, 2, 3 away. Looks pretty darn good. The last part, find the zeros of your equation. Well, to find the zeros, we'll do this one in red. To find the y-intercept, we replaced x with 0. To find the zeros, or the x-intercept, we replace y with 0. So y equals negative, I'll keep that 1 in there this time, x plus 3 squared plus 4. Okay, so step 1, subtract the 4 from each side. Step 2, undo the multiplication or division. Gives me positive 4 equals x plus 3 squared, and I'm out of room, so we're moving over. To undo the square, we introduce a square root onto each side, like so. Square root and square cancel out. We know the square root of 4 is 2. We did that previously today. And to finish this off, subtract 3 from each side. This gives me, this is weird with the two negatives right here, negative 3 plus or minus 2 equals x. However, to really have useful x-intercepts, we should write this as two different equations. One where x is equal to negative 3 plus 2, that's negative 1. And the other where x equals negative 3 minus 2, which is negative 5. X is negative 1 when the y was 0, or x is negative 5 when the y is 0. Let's get those plotted. Negative 1 comma 0, negative 5 comma 0, and now it's complete, that parabola. There's 1, and there's 2. Last but not least, we do need the domain and range. The domain shouldn't shock you. It's all real numbers. You can use that cool fancy double bar R, whatever sounds good to you. You can write it out. You could even do that interval notation like so. The range is always the tricky one. The range measures how tall your graph gets. The tallest my graph gets along the y-axis looks to be 4. The lowest it gets, those arrows mean it go down forever, is to negative infinity. So one way we can write this is that the y values are less than or equal to 4. The other way we can write it is we say we go from negative infinity to 4. We always put the smallest number on the left. We can't include negative infinity. That's not actually a number. We can include 4, though, because we do actually get to 4, right? There is a solid point up here with 4. So we have 1 down. Let's make sure we can do the next. Given this equation, state the vertex. Here we go. Positive 2, negative 5. You'll notice that these graphs change each time. We do our best to make sure that your parabola will comfortably fit in the middle of the graph just to make sure there's room for everything. So as a heads up, if you find you're graphing something and it's like way over here, then you probably made a mistake. Or we got lazy and didn't give you a nice graph. Either way. What's our axis of symmetry? Well, it goes through the x-axis at 2, matches the vertex. A value is a fraction. This one's trickier for sure. 1/2 over 1. Our a value, in order to use it to find more points, always needs to be written over 1. So I'm going to go up 1/2 to the right one, up 1/2 to the left one. Warning, if you go up 1 over 2, you will not get points that are on this parabola. They won't work. You'll see that shortly. Let's do the y-intercept. Y equals, we need that set up, 1/2 of 0 minus 2 squared minus 5. You can certainly use your calculator from there. I'm just going to do some mental math though. Negative 2 squared minus 5. Negative 2 squared is 4. Half of 4 is 2. And 2 minus 5 looks like negative 3. So when x was 0, y was negative 3. 1, 2, 1, 2. So we have the start to our parabola. Looking pretty good. And notice that up 1 over 2 certainly couldn't be on our parabola because then it would go straight up and that wouldn't be a function anymore. Last but not least, let's find those zeros. Okay, very similar to before. 0 equals 1/2 times x plus, I think it might be minus, yep it is, x minus 2 squared minus 5. Add 5 to both sides first. Oops. Then we have to deal with that 1/2. But we've learned before that to get rid of a fraction, we can actually go through and multiply by its reciprocal. I'm going to rewrite that so I have a little bit more room. The reciprocal of 1/2 is 2 over 1. Well, 2 over 1 on the right, we have to do 2 over 1 on the left. 2 over 1, though, is just the fraction 2. So this gives us 10 equals, these ones cancel, x minus 2 squared. Now we introduce that square root, plus minus. I don't know the square root of 10, don't say 5. 5 times 5 is 25, not 10. So we just keep it. It stays plus minus the square root of 10 equals x minus 2. From here, we should probably add the 2 to both sides to positive 2. And we have our x's. But we run into that same issue as before. Let's see these as two different equations. X equals 2 plus the square root of 10. X equals 2 minus the square root of 10. So just like before, we should probably go ahead and actually find decimal approximations here because we want a graph, right? We do have the exact x-intercepts. We can totally put those down here. You kind of have to write a little small. We know one of them is 2 plus the square root of 10, comma 0. And the other is 2 minus the square root of 10, comma 0. But that doesn't help me for my graph up here. So let's find those decimals. 2 plus, 2 minus. So first one, we have 2 plus the square root of 10. There's one of them. I'm going to get the other at the same time, though. And that's going to be our 2 minus. We're just going to copy that one down here, change it to a minus. And there we go. 5.162. 5.162, comma 0. And I think the other one was negative 1.162. All right. And let's make sure that holds up to our graph. 5.162, it's a little bit bigger than 5. And negative 1 point something, a little bit smaller than negative 1. Yeah, I think that kind of lines up with our U-shaped graph. So finishing this off, see our one nice parabola, and here comes the other. Great. Domain, we know that's going to be our all real numbers again. And then on to the range. See, the lowest it looks like this graph gets is negative 5, and you might start to realize that that definitely relates to the other value of the vertex. Negative 5 is the lowest it gets in this case. We say y is greater than or equal to negative 5. Or we can go from negative 5 to infinity. All right, so we've really finished up our parabolas at this point. The last part of this is going to be the average rate of change. Now, we first encountered average rate of change last unit in topic 6 with exponentials. Each unit before that, for topics 1 through 5, we had really talked about the rate of change. And the rate of change, of course, measured the steepness or the slope of our graphs. But all of those first 5 units, we were dealing with linear graphs, which had a constant steepness. This semester, topics 6 all the way through 10, deal with curvy graphs. Every point on those graphs has a different steepness. So we say those graphs do not have a constant slope or rate of change or steepness. So instead of discussing the actual slope or steepness of a graph, we discuss the average rate of change or steepness of the graph. And to do that, we just pick 2 points, and it can really be any 2 points. They'll be given to you, and we'll measure the average rate of change between those. Really, that's just finding slope between 2 points. Now, on this last page, at the very top, you have kind of like a key or guidelines on how to find the average rate of change depending on the situation. We're actually going to fill these in last, but they're nice to have here for when you go back and need help on your homework or your quiz or something like that. So essentially what's going to happen on this page is you're going to be given 3 situations where you need to find the average rate of change. The first situation is graphically. And if you're given something graphically, it means they will give you a graph, and you have to find the average rate of change there. The second situation is tabularly. It's always a tough word for me to say, and that means that they are going to give you a table of values. And from that table, you need to find the average rate of change. Last but not least, you are going to be given some sort of equation, and so we say we are going to find the average rate of change algebraically. I tried to list these in what I think is probably easiest to hardest, or at least least work to most work. So we'll start with graphically. So the very first thing that any average rate of change problem is going to do is it's going to give you an interval upon which we're going to measure the average steepness. Now our intervals are always given using x values. And in particular, we can always write those intervals as a starting point and an ending point. So let's look at A. It says from x equals 1 to x equals 3. Well, what that means is from a point 1 comma something to a point 3 comma something. To complete this point, and this will be the same for every problem, we need the corresponding y values. To do that, on this situation, graphically, we are shockingly going to look at the graph. So x equals 1 and x equals 3. Now I'm just going to focus on x equals 1 for a minute. X equals 1 actually has an infinite number of points, right? This point up here is the point 1 comma 5. This is 1, 4, 1, 3, 1, 2, 1, 1, 1, 0. We have all the negatives, and we even have points in between. So which of those y values is going to go with this point? Well, hopefully you said, well, since we're talking about the graph, it needs to be the point on the graph, and you're 100% correct. What we do is we identify the x value first, which was 1, and then we say which point along this line is actually on the graph, and that is the point, in this case, 1 comma 1. So I'll fill in this over here. Then we do the same thing with 3. This one goes faster. X value of 3, what is the y value that puts us on the graph? Well, that is certainly 2. So 3 comma 2. So what they're asking us here is to say, what's the average steepness from this point to this one? And so you'll notice that it's not very steep over here, gets steeper, steeper, and steepest at the end. The average steepness is kind of like the steepness in the middle, but it won't be exactly in the middle. And the way we do that is how we always calculate slope from a graph. We just count the rise and the run. Looks like we rise up 1 and run over 2. And so our average rate of change here is 1 over 2. And it's probably not accurate to put m here, but that's what I'm going to use for now. You'll see other notations. Sometimes you'll see a little bar over the top that sometimes means average, but I'm just going to stick with m. Everyone will know what you mean. All right, let's look at a couple other notations because this problem doesn't really get any harder. It just might be phrased in different ways. For example, they might say from -1 to 3. And you might think that that's the point -1 comma 3. But -1 comma 3 is up here. That point's not even on the graph. And so we need to remember that at times intervals can be given with these closed brackets. That means start at an x value of -1 and end at an x value of 3. Well, that's actually pretty nice because we know the y value that goes with that is 2 from earlier. So I think we just need the x value from -1. So if I look over here, an x of -1 looks like it gives us a y of 2. All right, so let's find the rise over run between those 2 points. And I know mine is easier to erase on than yours, but I think you'll be okay. We need to find the rise over the run, so how far up, how far over? Well, the run is easy. 1, 2, 3, 4. What about that rise, though? Well, I think looking at that rise, it looks like we rise up 0. And so our slope here, our average rate of change, is actually just going to be up 0 over 4. Though you wouldn't actually see that on a test as an answer choice because they would reduce that. What is 0 divided by anything? What is $0 split amongst 4 people? Well, that would just be 0. Okay, let's look at the third one. From -3, which is less than or equal to x, which is less than or equal to 3. This means x is all the numbers starting at -3 and ending at +3. Hopefully you can see the 2 points here. One of them has an x of -3. One has +3. And again, +3 goes with 2. Where does -3 go? Let's see, -3 is over here. Oh, it's way up there. It's 5, isn't it? Okay, so we have -3, 5, and we'll just count that rate of change. Looks like we go down 1, 2, 3, negative because we went down, and over 1, 2, 3, 4, 5, 6. There we go. And finishing this up, down 3 over 6. And also that would not be an answer on the test because we would reduce -3/6 to, of course, -1/2. All right, problem 2, tabularly. Well, the setup is again the same. So I am going to write a little bit smaller here. We strangely need a little bit more room, so bear with me. Maybe you can watch me write for the first part and then decide how much room you need. But let's go through it. A table of selected values of a quadratic equation have been provided to you below. So there are 4 points, it looks like here. Do you see the 1, 2, 3, 4 points? If you were to graph those 4 points, you should be able to make a U-shaped graph, or maybe an upside-down parabola, through them. We're going to use this table to calculate the average rate of change on a given interval. Well, A gives us some x values. It tells us we're going from -2, something to the point 3, something. Those are the x's. Well, when we had a graphical situation, we just looked at the graph to find the y's. How are we going to determine the outputs, the y values, from a tabular situation? Well, hopefully you realize that the x's, which are of course the inputs, right, are on the top row, and the outputs, which are sometimes known as f of x, but also y's, are on the bottom row. And so all we have to do is say -2 goes with 1, and 3 goes with -29. Great. We have our points. But then the nice advantage of the graph is when we had our points, all we had to do was count. I don't see a graph for this one. And in fact, a graph might be a little obnoxious because I don't want to create a graph that goes down to -29 or especially -125. So thinking back to when we found slope, is there another way we could find the slope, the rate of change between 2 points without a graph? And hopefully you're saying, okay, yeah, we had a formula. M equals, we had that fraction line, right? And then we had something subtracting on the top over something subtracting on the bottom. And the way we remember what is we think slope is rise over run. The rise on the top, well, think about it, which axis rises up and down? That's the y-axis, so the rise is the y's. And then our formula went y sub 2 minus y sub 1. The run, the x-axis, runs side to side, and so we have our x's here. Okay, so then if we wanted to use this formula, which we do in order to find our average rate of change, and you might want your calculator handy unless your mental math is pretty good, we're going to label these points. -2 is an x, 1 is a y, 3 is an x, -29 is a y. Points always go x, y. -2 is the first x that I came to. Y, or rather 1 is the first y. 3 is the second x, and -29 is the second y. And now we fill them in. Y sub 2, the second x we got to was -29. And I said x, but I meant y, and the first y we got to was 1. second x is 3, first x, negative 2. And we go through. Negative 29 minus 1 is negative 30. 3 minus negative 2 is 5. Negative 30 divided by 5, well, that is negative 6. So although this first one that I just boxed is an acceptable answer, if this was on a test, you would almost certainly see that reduced to negative 6. Let's try one more. This one gives us x values over an interval, negative 2 to 0. So negative 2 comma something and 0 comma something. Let's see, negative 2 certainly goes with 1, and 0 also goes with 1. Oh, that's nice. Okay, let's use our slope formula, and I always use parentheses. I don't think too many people do, but I really think that helps you from making mistakes with our negatives. x1, y1, x2, y2, looking pretty good. Let's see, y2 minus y1 over x2 minus x1. 1 minus 1 is 0. 0 minus negative 2 is positive 2. And so we have our answer. We could also reduce that. We saw this in the previous question, the graphical question 2. That reduces to 0. Ta-da! All right, third and final situation. We'll fill in the key at the top, and we're done. Sometimes, instead of being given a table or a graph, you're just given an equation. This is clearly a quadratic equation. Quadra, we have a square. So let's see what they're asking. When I did this one in class, I actually needed the space down below as well. So you might definitely have to write a little bit small. This one requires, I think, the most work. It's not terrible, but the most work. So, given the function, find the average rate of change on the interval from negative 1 to 2. So, negative 1 comma something and 2 comma something. All right, I'll leave a little space here. There we go. Well, we have x's, but we're looking for y's. And when we had a graph, we looked on the graph. Table, we looked in the table. Algebraically, maybe we should look in the equation. And sure enough, we need to remember this says f of x equals x squared minus 3, but f of x can always be replaced with y if that makes you more comfortable. So what that tells you is we can create y values by squaring the x and then subtracting 3. So let's create some y values. And our notation, I'm going to practice that f of x notation, it's good for us, says to do f of an x value. We have an x value here, it's negative 1. F of negative 1, the formula that's going to happen on negative 1, says take negative 1, square it, and subtract 3. Right? We just took the formula over here. And so, if we go through, negative 1 squared is 1. 1 minus 3 is negative 2. And therefore, our output is negative 2. Let's try one more. If we want to turn 2 into a y value, not negative 2, 2, then we find f of 2. 2 squared is 4, and 4 minus 3 is 1. So sometimes, and we're going to use this space down at the bottom to do our slope formula, sometimes you'll actually see this slope formula written a little bit differently. We were given the x values to start, and I'll do the second x first, so it's 2 minus negative 1. But then instead of putting the y values, they'll just use function notation, and they'll say f of 2 minus f of negative 1. Notice these match. Right? We could have written these formulas, or I'm sorry, these points that way too. This is 2 comma f of 2, because f of 2 is 1. And same thing in green, this is negative 1 comma f of negative 1. Now, we did the math to find those values. F of 2 was 1, and f of negative 1 was negative 2. But don't be surprised when you start seeing your slope using that function notation. It's very common at the upper level. You don't have to do it that way, but it shouldn't surprise you. 3 over 3, which reduces to 1. All right, last one. We'll do that same setup. There's an x of 0, and there is also an x of 2. Okay, so that means that my output will be found by doing f of 0. This output will be found by doing f of 2. And if you wanted to label these, we have our first x, our first y, our second x, our second y, and which means we could do our slope formula and find f of 2 minus f of 0 divided by 2 minus 0. Well, in order to do that, I mean, the denominator 2 minus 0, that's just 2, but we still need to figure out what f of 2 and f of 0 are. Now, luckily, we did f of 2 earlier. I think f of 2 ended up equaling 1, so we can probably shortcut that. We know f of 2 equals 1, so that's nice. We do still need to find f of 0, though. So f of 0 in this case, we use that same function from before. It's called f of x. So we're going to do 0 squared minus 3. 0 minus 3, which is negative 3. So f of 0, negative 3. 1 minus negative 3 is 4. 4 divided by 2 is 2. Whew, covered a lot today. Well, let's summarize and get you out of here. All right. If you are given a graphical situation and you're asked to find the average rate of change, the first thing they're going to do in any average rate of change situation is going to give you an interval. And then you're going to need to complete that interval by finding the two endpoints, right? So they're going to give you x comma something and another x comma something. You need to find the y's. How do we find the y's? Well, find these two endpoints by using the graph to find the y values. That's not too bad. Then we calculate the average rate of change, our slope, by doing the rise over the run. And I'm just going to say count on the graph. No real math you have to do there. Last but not least, if you are given a tabular or algebraic situation, same idea, you're given x comma something and x comma something, we need to start by finding the y's. How do we find the y's? Well, by using the table or the equation to find the y values. Right? Then we calculate the average rate of change. So you could see that as our slope formula, x2 minus x1, and if it's the equation, you might see f of x2 minus f of x1, but you're more used to seeing that as y2 minus y1 divided by x2 minus x1. And that's that. Now this actually works for any type of graph, whether it's linear, though that's kind of a silly situation, exponential, quadratic, or any other graph you study. If you're ever asked to find the average rate of change, there are 3 good, solid examples on here to help you out. So thank you for tuning in today. Don't forget we also found the zeros of parabolas and focused on those key components. This does conclude topic 7, and I'm excited to have you back for topic 8, which are going to be our polynomial operations and the big F word, factoring. So see you guys in a while, and I hope to get topic 8 up soon.